Okay, everyone, it is 11 o'clock. It is time for our last session of the day, which is a tutorial by Roland Haas. I would like to ask everyone who can, particularly the maintainers, to call in tomorrow, especially for the discussion of the future of the ET in the afternoon, or from 11 o'clock. I'm hoping at that time we can just sort of talk about what people would like to see in the toolkit in the future, what kind of directions the community would like to see us go, and what they think about where we're going. So I encourage everyone to come back tomorrow for that. Roland, are you ready?
Should be. Thank you.
So Roland, okay. So Roland Haas is one of the biggest contributors to the Einstein Toolkit that we have. He's a maintainer. He is a research scientist at University of Illinois, and always has very insightful things to say. Okay, you're introduced. Roland.
Right. Thank you for the introduction. So let me know if you can't hear me or if I'm going too fast or too slow. I can see the chat. I can't see hands up. So somebody will have to tell me if there's any hands up. Okay, with that said, thank you for having me. So I thought I'd give you an introduction about the Cactus reduction interface, which you can also find on the tutorial set in the server. Let me quickly show you where that is, if the browser lets me. So if you go to the main page, then you'll find a notebook named Using the Cactus Reduction Interface.ipynb. And if you click on that, you'll see the same presentation that I'm currently showing. It's part presentation, part actually a tutorial where I have things that you can execute. Let me hide all of that stuff. I can see things. So this is what I want to do. Basically give you an introduction how to use the reduction interface, both the basic usage, but also something a little bit more advanced. So with that, this is the notebook. The beginning of the notebook is the very same as for the notebook for the Einstein Toolkit tutorial that Steve Brandt gave earlier this week. If you have done that, then this is fine. Otherwise, you can execute this and you can use the notebook from scratch, and it will let you compile the code and then run a small test case. So let me scroll to the first actual new slide that you haven't seen before. And that would be, let me see, the reduction interface inside of Cactus. So to give a bit of idea what this is, what we call reductions in Cactus are basically operations that take the data that you currently have on the grid, say, for example, the density, and reduce these down to a single scalar quantity. The naming comes from the MPI function, MPI reduce, that does the same thing. And the reductions that we typically offer and that typically would be used would be something like compute the minimum over the grid or the maximum. You can also compute norms, the infinity norm, the 1 and 2 norm, for example. You can also compute things like the sum or the average, which are a little bit different in a sense of that they compute sums, and all of these sums, in fact, all the sums that appear in the norms as well, will always be volume weighted, which means that it will always be multiplied by the volume of the particular cell that the value is in, which is important for mesh refinement. And that means that, in fact, the sum reduction gives you something that's almost the Riemann sum. And it's almost the Riemann sum for a reason that the volume that's used is the relative volume of a cell, because Carpet, the driver, has no idea what the actual physical volume of the cell is. So you're off by a factor of the volume of a cell. And that's what's spelled out here. So if you look at it mathematically, then if you compute the sum norm in Cactus of a variable rho I, where I is the grid point index, then it actually computes the sum over the value of rho at a particular point times the volume of the grid cell, delta Vi. Then once it's done, it effectively divides everything by the volume of a cell on the courses grid. That's what you get number-wise, which means, of course, if you turn that around, you multiply everything by the volume of the coarsest cell, then you're down here. And it means that if you take the sum reduction, you multiply it by the known volume of a cell on the coarsest grid, and you crank up the resolution to infinity, then you actually get back the integral of rho over the whole simulation volume. And that's the reason why everything is volume weighted. So that's kind of the two types of things that you have. You have minimum and maximum, and then you have got these sum type reductions. The available reductions, and on the table here, I show a couple of them. They are not prescribed by characters, but instead it depends a little bit on what driver you're using and what reduction tone you're using because of that. So for example, the pug driver will call the reduction that computes the minimum min, while the thing is called minimum in carpet, and max for the maximum versus maximum in carpet, the others agree. So you have to be a little bit careful. So that the exact set is determined by the driver, not so much by Cactus. Some things are missing, particularly if you're used to MPI. What's not there is an equivalent of MPI's minlock and maxlock operations that would let you compute the minimum or the maximum of a grid, and also know which processor, MPI rank in particular, owns that particular data point. That is not provided in Cactus. Okay, that's kind of my quick introduction of what reductions do. They are typically useful for analysis things, but in particular the sum, because it becomes an integral, is useful for all kinds of things that you would like to do. For example, computing centers of mass, or total mass inside of a particular region, all kinds of things where this is useful, computing the ADM mass, all these things is where this is useful. So that's the high-level introduction. Now, how would you use this in your actual code? So using reductions, there's two ways that you can do that. The easiest way, if you only need a reduction as output, then you can ask Cactus to do all the work for you. In fact, if you set the parameter IO basic reductions to a particular set of strings among the table that I had there, then the output thorns will actually apply these reductions to the variable that you're asking for in IO basic outvars, and output these to disks, to disk as files. So that's the easiest way to use it. And that's how you can, for example, easily output the maximum of the Hamiltonian norm, the Hamiltonian constraint, for example, or the maximum density on the grid, if you just need it for output. If you need to reuse the reduced value in your code, or if you want to do something more fancy, you can actually do the reduction programmatically. And that's what most of this tutorial is going to be about. In fact, there's two ways you can do that. There is technically the newer and more modern way of doing things called CCTK reduce grid arrays, which is only supported by the pug driver. And then there is the older way that uses the CCTK reduce function here, that is supported by carpet and probably by pug, although I haven't really checked. So for our tutorial here, because carpet is in fact the newer driver, even though it supports the older interface only, we'll talk about CCTK reduce, and I'll give you an introduction on how to use it and what it does. So CCTK reduce is kind of the one-size-fits-all function to do reductions on Cactus grid functions. It's the only one that exists, and that's the one that you would like to use. So if you look at the documentation of what you do, then interesting. Why does this is not supposed to wrap around. Anyway, so this is the prototype of the CCTK reduce function as you would find it in the documentation. So it takes a whole lot of arguments, and I'll quickly go through them. So first argument is familiar. That's a Cactus grid hierarchy. That's normally CCTK-JH. The second argument here, where it says proc, that one specifies which MPI rank is actually going to receive the result of the reduction that mimics what MPI can do. Normally, you could give a particular MPI rank, or you can give the special value of -1, which means the result will be broadcast to all the MPI ranks, which is in particular useful if you want to reuse that number afterwards in computations. And the third argument actually tells it what to do. It's called operation handle. And you get this by calling this CCTK reduction handle function, which you give a string. So you give this one the string sum, it returns to you an integer, you pass that integer here, and that's the handle. There's no way to free them because it's really just a mapping of names to numbers. Then the next argument here, num outVals, is a little bit unusual. That is the number of output values that you expect to get per input field that you give to that function. In carpet, this will always be 1, which means each input field will give you exactly 1 output value. Operations that would give you 2 would be, for example, this MPI minlock and maxlock, which returns 2 values to you, the value of the maximum and the MPI rank of the processor that owns the result. But for us, it's always going to be 1. And the next one says the type of the output values, which usually for integer variables will always be int, for real values will be real. If you actually pass in a complex valued Cactus grid function, then depending on what you do, this might actually be a real, because if you're taking, say, the absolute value of a complex number, you're going to get a real valued number. And then lastly, there is an array outvals, which is a pointer to an array where all the output values will be stored. So it needs to be the proper size and it needs to be the proper type to hold either these real or integer values and one value per num outvals. Then second to last argument is actually this num in fields, which tells Cactus how many grid functions do you want to take a reductions over. Maybe you want to do it for more than one grid function at the same time, maybe for all the components of the momentum constraint. And usually, as is typically the case in Cactus, it's faster to give it lots of work. So it's faster to do a call to CCTK reduce once with 3 grid functions rather than doing it 3 times with 1 grid function. And then the last bit here that says ... that's actually the C syntax, because this function is a C variadic function. So it takes any number of extra arguments, and the extra arguments are the variable indices of the grid variables that you want to do a reduction of. So if you have 1 grid variable, you give 1 variable index. If you have 2, you would give 2, and essentially the number must match up with this num in fields. And that's the prototype of the reduction function. And in some sense, this is really all there is to it. And I could stop and could say, this is how you use it. Fortunately, this is not quite the whole truth, and there's going to be a bit more complication. And I'll go to that. I'll explain this in a little bit. So let me first show you a very simple example use. So I hope this fits the screen, yeah, roughly. This is a very simple code that will use the sum reduction over the variable GHydroDense, which is the relativistic rest mass density. And that means that if you integrate over it, given that there's a volume factor in there, you're going to get the relativistic rest mass. So that's the formula that we are actually computing. The relativistic rest mass is the integral over the relativistic rest mass density times the metric determinant, which is already included in GHydroDense, over the volume element. And that's the code. You can see there isn't all that much. First line, we are getting our summation handle. We do some error checking. Next line, we are getting the actual variable index of the GHydro variable. Then I'm going to get myself some buffer to store the result, and I'm going to initialize it with some known value to make sure it actually happened. So 42 is unlikely to be the actual result of the reduction. And then I'm calling the reduction function here. Gets CCTKGH. I would like the answer everywhere on all the MPI ranks. Calling a sum reduction. I will expect 1 output value per input field. All the output is going to be real valued, so that matches CCTK real. I'm passing it a pointer to my output buffer, which is my rest mass. And I have 1 field that I want to compute a reduction over. And I'm passing 1 variable index because of that. And then I'm checking for errors, and I'm outputting things to screen. And if this runs, and if this thing works properly, then you should get just a relativistic rest mass of the system. That's the C code. You actually have to tell Cactus when to run it. And since a reduction is inherently a global quantity, it always looks at the whole grid. Any scheduled function that calls these reduce functions has to be scheduled really in global mode. There's some leeway, but mostly you want to be in global mode. And therefore, this is the schedule statement. I have a function that I might call rest mass compute rest mass that I'm scheduling in the analysis bin because we analyze something. And I want this to happen in global mode, which means it happens once per time step and has access really to the grid scalars only and not directly to the value that's on the grid. All right, that's the simple use. That kind of tells you how you can do a reduction, assuming you already have the things you want to reduce over on the grid in a variable. If you don't have that, if you have to compute them, then you have to do some work to actually compute the thing you want to integrate or reduce over first. And that's typically the hard part. So let me give you an example how this works. This is the simple case. Assume we want to just compute this by hand. And then the official way of doing that and the way that Cactus was designed to do is, well, suppose you want to compute this by hand, then you have to schedule a separate function. Suppose a function called rest_mass_row, which now I'm executing once per iteration in the post-step bin. And this is a local function because it actually has to compute something on the grid. That's the traditional way of doing it. This will work. There is a caveat here, and the caveat is that if you do this, then the grid function that you want to integrate over has to be computed every single time step. You can't skip some. It must be done all the time, even if you don't need to compute a reduction at that point. You also need to keep 3 levels of time levels around for this. And then finally, because you have 3 time levels for that function, that grid function also needs to be checkpointed. And that's just a function, just a consequence of there being 3 time levels. If you violate any of these 3, then chances are that you either get an error from cctk reduce if you're lucky, and if you're unlucky, then you get slightly incorrect answers. And this seems like a strict requirement. Why is this? Where does this come from? And as many things that are complicated in Cactus, this comes from mesh refinement and in particular subcycling in time. So the reason how this happens is basically in the diagram that I have here. So if you have subcycling in time, then the different refinement levels exist in different times only. So not all the grid might exist at every single time step, but only parts of the grid might exist. Also, the sum reduction has to take the relative size of the grid into account. So what would happen is the following. If you are in a situation like what's shown in this diagram, where you have say 2 levels of mesh refinement, the black one, which is level 0, the coarse one, and the blue one, which is the fine refinement level, level 1, for a particular variable row with 3 time levels. So I'm showing you what the time is that corresponds to each time level. So if you look at the coarse one, the oldest version of the coarse time level corresponds to time 3. The next older one, next newer one is t equals 4, and the newest one would be t equals 5. For the refinement level 1, timing would be different. The oldest one would be 3.5. The past one would be 4, and then the current one would be 4.5. And the way that things work is if you now want to compute a sum reduction at t equals 4.5, meaning on this blue level where the error comes from, you have to work a little bit harder. So the reduction is an integral over the whole grid. And the part of the grid that's the blue line here, that one is easy to do. You just sum over and you get an answer. If you now stop there, then your sum would really only be over that grid. So it wouldn't really converge to anything useful because you would only integrate over a part of the grid, and you get an answer that would be very confusing because you really only look at half the grid. So what you need is you need to somehow come up with values that corresponds to the spatial regions where only the coarse grid lives, but at the time where the fine grid lives. So what that means is you have to take the values that exist on the coarse grid in different times, in the past, here, and a little bit in the future actually, and interpolate those in time to the same times that you want to get the answer on, and then also integrate that into your sum. And that's the reason why you actually need 3 time levels. That's also the reason why you have to do that every single time step, because you need to have these past time levels around. So if you decide you want to do a reduction here, you can't compute just row on the current time level because you need the past time levels as well. And that's where the complication comes from. And that means that if you want to do it in the traditional way, for every single thing that you want to compute a reduction on, you have to allocate a grid function with 3 time levels that exists for all times, because you have to have it around and do the reduction and have to pass 3 time levels. So that means if you are tempted to compute your reduct on the fly, like so, then you're going to run into trouble. So suppose you would like to do something like this. So we want to have a situation where we don't have to store all the data all the time, but we want to compute only what we need when we need it. So in some sense, we want a schedule, like a setup like this, where we have the first block here, where we compute our integrand, say the density, everywhere. And then we call a reduction, and then we output that to screen. That's what we want. That actually works if you're using Pug. It doesn't work if you're using Carpet because you have mesh refinement. And the reason why this doesn't work as well, it violates the picture that I have shown you before, You can either schedule yourself in global mode, in which case you can actually call the reduction function, but you don't have access to the grid function pointers, so the loop will fail. Or you can schedule yourself in local mode, in which case these loops will work, but you will be unable to actually call the reduction because you would only compute the values on a single grid, not everywhere. And also there is a situation where you might have more than a single component, more than one component owned by a single MPI rank. So different MPI ranks might actually call this reduce function different numbers of time, and then you get an MPI hang. So this doesn't work. And there's no way in Cactus really to easily fix this. The way to fix this is to step back a little bit and realize that this happens because you're dealing with mesh refinement and you're actually doing something more advanced here. And that means you end up having to use more advanced methods. In this case, you have to use Carpet's mode changing macros. So these are macros that Carpet provides for user thorns to actually programmatically walk over the whole grid, over all the refinement levels, over all the llama coordinate patches, and over all the individual components grid patches that are owned by a particular MPI rank. They are provided in Carpet's public header file, carpet.hh, which you can include, and then you get access to these macros. The ones that I'm listing here are the ones we're actually going to use. There's more, but these are the ones that we are going to use. There is basically a macro that says begin ref level loop, and that lets you loop over all the refinement levels from the coarsest to the finest that exist in the simulation. Then after that, you have to loop over all the llama coordinate maps, the different coordinate systems that exist, and loop over all of these. Once you're in a particular coordinate map, now you can actually start looking at individual grid patches, local components in this case, that are owned by a particular MPI rank, and work on these. And only then do you actually have access to the individual grid function pointers using the declare CCDK arguments macro. And it turns out that this is exactly the same code logic that Carpet internally uses when it actually walks the schedule. So you're doing exactly what Carpet is doing, and therefore you should expect to get the same answer. So this is the way to do so. It makes your code a little bit more complicated. I'm going to show you what the code looks like. So in here, I have the equivalent of the code of my wish list, only that this time it actually works. So this is the code fragment that you would want to use. You have to first include this Carpet header to get access to the macros. You start off in global mode. Then you enter a loop over all the refinement levels, starting from the coarsest level going to the finest level. On each level, you loop over all the individual coordinate maps, asking for access to really only the grid functions. Then in each map, you loop over all the grid patches that are owned by this particular processor. And once you're there, now you're in effectively local mode, and you can use declare CCDK arguments to get pointers to all the grid functions on the grid. Then you can loop over your patch as usual. So loop over all the points in my grid function patch, get an index into the array, and then set some temporary variable to some value. And you can see here that I'm actually doing it for the current, the past, and the 2 times past time level, so that all 3 time levels that I need are initialized properly. Then you unwind everything, you go back, you end up in global mode, where you can call the reduction interface again, and you get your answer back. And this fragment now would work in Carpet. And then I show the schedule, looks fairly similar. There's still only going to be a single schedule function in global mode. And please ignore the storage statement here. I was hoping that would work. That doesn't quite work. So that's the way to do it. And in the end, it is not that much more complicated than doing the naive way, but there is a little bit of extra work to it. So, and that's basically the end of the more lecture type thing. So the remainder is going to actually take this information, put it in a thorn, and write an actual thorn that would compute the center of mass of a matter distribution, pardon me, on the grid. Right. So let me scroll down a little bit. So this is what we would like to do. The example code that I have for you is a code that will compute an approximation for the center of mass of a matter distribution on the grid, computing these mass dipoles, mi, which are basically really just the density multiplied by the position integrated over all of space. Then it computes a normalization condition, which is just the mass density integrated over all of the volume. And then you normalize and you get a center of mass coordinate by dividing this mass dipole by the mass monopole, the kind of a total mass. And then it depends a bit what you throw in there. In the example, I'm just going to use hydrobase rho, the rest mass density. Note that there's no relativistic in that word, for rho. And that means that my mass that I'm computing isn't really any proper mass. It's not the ADM mass. It's not the relativistic rest mass. It's just something that's an integral over a density. And it's not the same thing because it's missing a relativist, it's missing a metric determinant here. So it's good enough to get a center of mass. So that's the idea. So I'll try and see if we can all, if this all works and if people can follow along. So if you find that I'm going too fast, please say something in the chat or raise your hand, and hopefully someone will notify me that I'm going too fast. Right. So creating a new thorn in Cactus is typically done by using the special make target new thorn that exists in the Cactus make file. And that one creates for you a skeleton of a proper Cactus thorn, creating all the files that you would need. So all the CCL files, a documentation file, and the README file, so that you can fill in the blanks. The thorn that it creates actually compiles. It doesn't do anything because really it's an empty thorn. So if we were in a shell, then I would ask you all to run make new thorn, and you would get your new thorn. That doesn't work in a tutorial notebook because I don't have a way to actually input anything to any questions that the new thorn target asks me. So instead, what I do is I kind of script the interaction with the new thorn target with some Python code. And that's what's happening in the next cell. So if one looks at what the script actually asks me, then you can extract prompts and you can code up answers for those prompts. So here, when I'm being asked for a thorn name, I'll say I want to create a thorn called center of mass. It'll then ask me to pick one arrangement to put my thorn in, and I'll say I want to put it in the Einstein analysis arrangement. It'll ask me for an author name for the thorn, and I'll put in my name, Roland Haas. It'll ask me for an email address, and I will put in my own email address, in this case rhaas@illinois.edu, after which I will be asked if I want to add another author, which I say no. And then it will ask me for a license. And for now, I'm just going to pick the GNU public license. So this one, so far, it doesn't really do anything. It just sets up a dictionary of prompts and answers. And then in the next cell, I have a bit of Python code that actually feeds this information to the script. It's a little bit complicated, but the important pieces are basically that I have this remove line here where I first get rid of any existing thorn by that name, so that you can try this a couple of times. And then in the second line here, I actually call the new thorn script, creating a pipe. And then I'm looping over all the output that the script produces, feeding it answers. The code is probably somewhat dense and not terribly understandable, but it logs everything that it does to screen, and we'll look at the screen output, which is more useful. So I'm executing this now. And you can first see, okay, I've tried this before. It actually tells me that it's deleting my existing thorn, which is fine. And then the script actually starts to run. It'll start saying that's creating a new thorn, and it's going to ask me for my thorn name. And I had coded up that I want to name my new thorn center of mass. It then lists me all the existing arrangements that are there. And it will ask me to pick a new name for my arrangement or pick an existing one. In this case, I say put it in the Einstein analysis arrangement, which already exists. Then it asks me for the thorn author name, which is my name. And then finally, for an email address, where I put in my own, asks me whether I have another author. I do not. ask me what license I want, and I say, well, I'd like you to do the GPL method, GPL license, and then finally the script will say that it's now creating a thorn, at which point I consider the whole chat done and the script ends. So that's how the script works, and that's how you can create this more or less automatically. Now, what the script does is it creates all the files for me, and I have to fill in the blanks. We could look at them. Here, I'm kind of providing you what you want to put in them in the end. A cactus thorn contains a couple of control files, CCL files, cactus configuration language files, usually interface.ccl, param.ccl, schedule.ccl, and configuration.ccl. And for my thorn, it's simple enough. I only need to provide a handful. So I need to provide an interface.ccl file, which defines what grid functions are provided by my thorn and what grid scalars exist. It also lets me specify what other implementations my thorn inherits from. For example, if I need coordinates, I need to inherit from the grid implementation that gives me the X, Y, and Z coordinates. I also need to have access to the hydrobase variable rho, so I need to inherit from the hydrobase implementation. And then finally, it's also the place where I can request access to any public header files declared by other thorns. In this case, this would be the header file carpet.hh. So if one looks at what I have this write file command that Peter had already used, and I'm writing to the center of mass thorns interface.ccl file. I'm choosing a name. In fact, that was already put for me there by the new thorn command. And I'm telling it what I inherit from grid and hydrobase. I want to include a public header file. So this needs to be users include header, which gives me a header file called carpet.hh. I want to declare a temporary grid function, rho xi, that I'm going to use for my integration. It's a grid function because it lives over all of the domain. I need 3 time levels, but since it's temporary, I don't want to actually checkpoint this thing. And then finally, I have 3 grid scalars in my center of mass group. So there's a scalar. They only have 1 time level. Sorry, I have 4 scalars actually for my total mass in some sense, and then the 3 center of mass coordinates. And these are all the variables that my thorn declares, nicely spelled out here. Then with these, let me actually execute this. So I have this one. The next file you need is a file schedule.ccl that tells Cactus what functions to actually run. And that one is going to be very, very simple. Again, it writes to center of mass slash schedule.ccl. In my schedule file, I actually need to schedule storage for my variables. So I need storage for center of mass, and I need storage 3 time levels of my temp rho xi variable. I also make sure that hydrobase rho has 3 levels of storage, just because I'll need them, and otherwise I run into issues that I could get a seg fault if somebody doesn't allocate enough memory. And then finally, I have my actual scheduled function. So now I have my schedule mass compute function, which is scheduled only in analysis. It runs in global mode, and it's written in C. So that's the second function that I need. I happen to not need a param.ccl file because my thorn is simple enough. There's nothing that you could change. So the only one that I still need is configuration.ccl. That one is maybe a little bit more unusual, and that is not so often used with Cactus thorns. So what I do here is the following. I'm using Carpet's internal macros, which means that my code will link against Carpet, which first of all imposes a link order restriction. I have to make sure that in the linking order, my code appears in the proper position. It's also a dependency of my code exactly on Carpet. So what I want to do here is I want to tell the Cactus build system, first of all, that I depend on Carpet, so that Carpet makes that the build system links me properly. And secondly, that when I am actually run, the runtime system will make sure that the Carpet thorn is enabled whenever my own thorn gets enabled. And that's what happens here. I can write to configuration.ccl, which is the Cactus configuration file that records these type of things. I can record that I indeed require the Carpet thorn to be present. And that's what will make sure that I can link against it and that I'm also having access to Carpet at runtime. And that's all the files that declare configuration items for Cactus. Let me execute those two. There we go. And that's the configuration for Cactus. I have to now provide my source code, and that happens to be just a single file, which is the file source compute.cc, which again wants to compute this mass dipole, which is the density times the position times the coordinate, as well as some normalization factor, which is just the density integrated over everything, and then I normalize things. So this is the code. Uses write file, writes to a C++ file. And it looks like a pretty much standard file. It has the typical Cactus headers at the beginning, includes ccdk.h, includes ccdk arguments, includes ccdk parameters, even though I don't have any. The next one is my actual public header file that I'm asking for from carpet. So that's carpet.hh gives me the macros. Then is my scheduled function. It's a C++ file, so I need extern C to make it have C linkage. And then it's the regular thing. Oops. Declare declare parameters. I currently don't declare arguments here because I would be in global mode. There isn't really all that much that I can do with them at this point. But I can get my reduction handle for my sum reduction. I can get the integer variable index for my temporary variable. And then I can actually do my reductions. So this is now a little bit more complicated because I don't need to do just one reduction. I actually need to do 4. So I need to do a reduction for the mass, for the x, y, and z component. And I'm cheating here. I'm treating these as a 4-vector as components of a 4-vector indexed by this variable c that goes from 0 to 3. And I'm going to loop over this. And in each of the loop, I'm going to compute first the mass, then the x, the y, and the z component. So I'm in my loop. I'm in global mode still. So I'm using begin ref level loop to go into level mode, starting from the coarsest level, then going to the final levels. For each level, I'm going to loop over all the coordinate maps that exist on this particular processor. For each of the maps on this processor, I'm going to loop over all the components that exist on this particular processor. And now I'm actually in local mode. And I can call declare ccdk arguments, which now gives me pointers to the grid functions on this particular component. And in the next line, I'm going to take these, in particular the coordinates, x, y, and z, and I'm going to form another 4-vector out of them that is going to be the coordinate that I multiply my density by. So it's a bit of a trick that you might see every once in a while, where I'm turning individual variables into just an array for ease of use. So now I have pointers for my coordinates. I can start with my loop over the grid. I can get a grid an index into my grid, just like this. And then I can actually compute my integrand. So I have my temporary grid function, temp_row xi, and I want this to be the density at that point. And then if it's the mass that I'm computing, in which case c is 0. When c is 0, this pointer is null. And if the pointer is null, I don't want to multiply by a coordinate. Instead, I multiply by 1, so that I'm just getting the mass. If I'm actually looking for x, y, or z, which means that the c variable is 1, 2, 3, then I get one of these pointers, and I'm actually indexing the actual coordinate. And this is done 3 times. Once for the current time, once for the past time, and once for the past time, time level 2. Then everything unwinds. I'm going out of my local component, out of my grid patch, out of my component, out of my map, out of my refinement level loop, and I'm back in global mode. At which point now I can actually say, okay, I would like to get function pointers again, but this time, since I'm in global mode, the only ones that are really usable are the grid scalars. So I have my 4 grid scalars, the mass, the x, y, and z components of the center of mass. That's here. And I'm doing the same trick. I'm going to form a 4-vector out of them just for the ease of writing my code. And I'm going to call the reduce function on them using all the information that I've collected. So it's ccdk reduce, grid hierarchy. I would like to get the answer everywhere on all the processes. I want the sum reduction here. 1 output value per input value. Everything is real valued. And this now is a pointer to the output variable. And that's the ones that I've set up here. M, Cx, Cy, and Cz are actually pointers to the grid scalar. So this one gives me the pointer back. There's one variable I want to integrate over, and it's always going to be my temporary function. So this is still inside of the loop over components. So it's going to happen 4 times, once for the mass, once for x, once for y, once for z. And then I'm done. This one here is the loop over the components of my 4 vector. And at this point, I now have computed 4 reductions with 4 different integrands computed on the fly, and I've stored the results in these 4 grid scalars in Cactus. And I'm almost done. There's one more thing I need to do. I just have the integrals. I actually need to make sure that the integrals are properly normalized. So I'm in global mode again. I'm getting declare CSDK arguments, gets me the grid scalars, and I'm normalizing the x and the y and the z component by the total mass that I've computed. And to make my total mass more interpretable, I'm actually going to multiply the total mass by the grid spacing on the courses grid here. And that turns this m into an actual integral rather than just a sum, well, just a weighted sum. And that's basically it. That's the whole C code that does the center of mass computing. All right, with that, it's pretty much done. There's one more file you have to do. You actually have to tell Cactus to compile your code. That's done in the make code defn makefile fragment, which is also provided for you by the new Thorn script. Just happens to be empty. So what I do here is I have to enter the file name of the file that I want to compile, compute.cc, as one of the sources to compile. And with that, I've got all the pieces together. Let me see if I forgot anything. So I've executed everything, I hope. Let me scroll up. Yes, I have. And we can now actually compute our new Thorn, compile our new Thorn. It's the same as you will see, hopefully being used by Josef when he gives you a tutorial. I want to add an extra line to my Thorn list. Again, if this was in shell, you would just use an editor. Since this is a notebook, I have to write some Python code that does this. And I'm just going to execute this and going to show you that, yes, at the end of my Thorn list, indeed, now I have an extra line that has Einstein analysis center of mass as the new Thorn. And once I have this, I can actually go ahead, I compile everything the same way that Steve showed you yesterday using SimFactory, 2 processes at the same time. And for kicks and giggles, I'm also going to measure how long this is going to take. Oops. So it's running. You can see that it's running here. And since I've already compiled everything, this should be fairly quick. Let's see. So are there any questions about anything that I've presented so far?
I don't see any hands raised, and I don't see anything in the chat, Roland. Okay. But I think a lot of this material it's really great. I think this is a kind of tutorial I've been wanting to have on the tutorial server for a long time. But I have a feeling that students may have to come back to it more than once to fully take it in.
Yes, it is an advanced tutorial, and I was kind of hoping to do this after Josef had given his, but I didn't check.
But the schedule didn't work out that way. However, yes, let me point out that that Friday at the moment is pretty much going to be a day for people to come and ask questions and work through details. I don't know. This will be an opportunity for you to get the attention of the developers. And I hope that you make use of it and come back and maybe ask Roland some questions about this. And I'm also hoping that some of this will resonate more with you after you hear Josef's tutorial. Right. After you hear things multiple times, I think it sometimes helps.
And I'll be very happy to answer questions. So this is done compiling. It took about a minute or so for me to compile. given that I had everything other than my thorn already compiled. So with this, in some sense, we are done. We have the code. We've written the code, and I promise you the code actually works. If you're naive, you trust me on this. If you aren't, you ask for a test case. And that's the remainder of the tutorial. I suspect I don't quite have enough time, which is a shame. Because in
You
some
have
sense,
15 minutes.
this is more important than the others. So let me quickly show you what a test case is. So Cactus has a facility to run test cases via a particular target, the test suite target. And that runs actually regression tests. So they are tests that are supposed to check that the code is still functioning the way that it was initially designed by the author. That means they are small and they are quick. There's about 300 or so of them. So each one should run in a couple of seconds. Otherwise, you're going to wait for a long time for all of them to finish. In particular, this means that the Cactus tests are not convergence tests. They are not physics correctness tests. They are not designed to do that to check that you actually get the correct answer, or necessarily that the convergence order is what you naively would expect. They're really tests that check if anything was broken. So that means that if you want to verify physical correctness, then this is something that the author needs to do when they write the code. And presumably what they've used to test correctness then turns into a test case because you already have written things, but probably with lower resolution or otherwise reduced functionality. We're going to do more or less the same. We are going to take some sense of correctness test, and we're going to turn it into a regression test because it's so simple. Right. So on the technical side, a Cactus test actually consists of two things. It consists of, a test parameter file, which we're going to write, as well as an expected set of output values that are stored inside of the thorn directory. And those are the ones that Cactus will compare against whenever you rerun the test and make sure that you still get the same numbers as originally recorded. There's a bit of leeway because Cactus is aware there is a thing like floating point roundoff, and not all processors are created equal. So there is a bit of fuzz in this comparison that you can actually control. So with this, let me repeat and restate this. If you design a test case, and you should for all thorns that you're writing, the test case should be simple, should be easy to understand, it should be easy code. It should be small in the sense of that the output files it produces should be small, preferably a couple of kilobytes, certainly not megabytes if you can do it. It should run very quick because there's many tests that all run after the other. It should use as few other thorns as you can possibly do, so it can be tested without having those thorns in your thorn list, which is required for simpleness. It should output as few variables as possible so that the output is small. Some of the clusters we run on have restrictions on the home file system size. It should only output norms and 1D ASCII data, because if you output anything else, it probably gets too large anyway. And it should finish quickly. I say here in under 1 minute, better even shorter for the point that there really are hundreds of tests that are being run. And if you have all of these, you have a decent test case. There's more to it. Please read Ian Hinder's very excellent adding a test case tutorial on the Einstein Toolkit wiki, which I've linked. And that has all of this information plus more on what's good practice to create a test. And with that, I'll show you what a test parameter file could look like, at least to some extent, probably not all of it because it gets a bit into technical detail. What we're going to do is we're going to take the TOV example parameter file from the original Cactus tutorial that you've run yesterday. That's a single spherically symmetric star that originally sat at the origin, and we're going to use that one as test data to compute the center of mass. Now doing so, we don't want this thing to sit at the origin because that would give us a center of mass coordinate of 0, which is way too easy to achieve by having a random bug in your code. So instead, we're going to move the TOV star so that it's no longer centered at the origin, but it's centered at coordinate x equals 3.5, y is 1.5, and z being 2 by setting Cactus parameters for the TOV solver thorn here. This then implies, that, where did it go? I'm sorry. This then implies that you have to also move the grid, because there's a grid hierarchy of 2 refinement levels that were centered on the star. If we move the star, we have to move the refinement layers like this. You also have to keep in mind that now you've moved the star away from the origin, so the symmetry conditions no longer apply. Now your system is no longer reflection symmetric around the origin, so the reflection symmetry thorn can no longer be used. We have to get rid of that thorn. We have to turn our domain from something that only covered the positive part of space to something that covers all of space. So now it goes from -24 to +24. That implies that the outer boundary is no longer a symmetry boundary, which means the shift out parameter is no longer 1, it has to be 0. And that's somewhat technical, but unfortunately required. That changes the domain to have something that actually is recognizable and that is non-zero. We actually want to enable my own thorn. So I want to activate my center of mass thorn. It has no parameters, so no parameters will be set for it, but it needs to be active. On the other hand, I want it to actually produce output that I can get. Since it produces scalars, I will use the IO ASCII 0D output to write this to disk. So I'm going to use Carpet IO ASCII's 0D variable output functionality, which outputs data on a single point, and there's a scalar that's a single point. And I'm going to output my whole group. That's the center of mass type of variables that I want to have to disk. And I'm going to do this every single time step. And I'm going to make sure that I get one file of output for the whole group rather than 4 files, each one with a single number in it. That's kind of the meat that tells you, okay, that's the physical setup that I want. That's the output. Then we clean up. Everything that I don't need is removed, and that's the list of stuff that I'm kind of removing from my parameter file, which is just something you try out and see when it breaks. And then I want to make it run more quickly. I said it should run fast. Sorry, my screen just turned off. Okay. Then the original parameter file you ran yesterday runs for about 10 minutes. And that's way too long, of course, to run as a test suite. So I'm going to reduce the runtime. I really only have to run for one full time step with 10 mesh refinement levels. A full time step of the coarse grid is 512 iterations on the finest grid. So that's going to be my maximum runtime. Just one step, that's sufficient. That means I get initial data, I get one time step, and everything should be fine. Plus a couple more settings that make things look nice and that are described in Ian's tutorial. And I'm just going to take for granted. The next cell here then has all of this actually in. So I'm writing a parameter file into the test directory, and I'm going to name it off-center tov.par. That gives me the parameter file. I'm executing this, and that writes it into my Thorn source code directory. That gives me the parameter file that's half of what you need. The other half is data that you say is good. So I have to somehow run Cactus at least once on this parameter file to produce data. We typically say one is supposed to use the simulation factory to run anything with Cactus. It has a test suite option, which is good to test the test suite, but it doesn't let you actually generate data. Same way Cactus has a target sim minus test suite that does the same thing, but is on the lower level of the Cactus build system that has the same functionality in there and has the same restriction. It doesn't actually let you generate the data. So we basically have to run Cactus by hand on the parameter file to get your data that you want to compare against. And that's what I am having in the next cell. Also shows you how this is done if you ever have a need to do so. You change to the actual test subdirectory of the Thorn. Get rid of anything that's already there. I want to run with 2 OpenMP threads, 2 MPI ranks, then the full Cactus executable, and the parameter file. And then once this thing is done, I'm going to output to screen the content of the 0D output file center of mass that was written by the code. So let me execute that cell. That's going to run. Oh, it's done. And it produces a whole lot of output. So that's all the Cactus output you would normally find in standard out, now to screen. And if you scroll to the very bottom, then you'll find that here it actually output the content of the ASCII file that was output with 3 lines of output for iteration 0, then iteration 256, which is kind of an iteration on the fine level, and then 1 iteration on the coarse level 512 with time information as well and information on what it found. So column 3 would be my mass integral, which is this, and this is not anything close to the total mass of the star, which would be 1.4, nor is the baryonic mass, which would be 1.5 or so. But the coordinates are correct. So I have a center of mass coordinate in the x direction, which is about 3.5, which is what I want, 1.5 in the y direction, and 2 up to round off in the z direction. So that actually seems to work, which is good. So this is in some sense a very simple physics correctness test that I've done. I've inspected my values, they look sane. This is at least good. You can now actually go ahead and you can say, okay, this is my data. Can I somehow check that it would fit into Cactus's test suite mechanism? And yes, you can. You can run the test suite. And again, I'm going to do this a little bit more simple than using SimFactory. I'm just going to use Cactus's sim test suite target to run a test suite with just the Cactus functionality. To make it a little bit more interesting, I'm going to take the data that was produced using 2 MPI ranks. I had n equals 2 above. And I'm going to test this using just a single MPI rank. And I'm also going to use just a single OpenMP thread to have some variation in there. And once more, if you were doing this on a shell, then you would say, make test suite, and you would answer questions that Cactus would ask you. I can't answer any questions, so instead I'm providing all the answers to Cactus in a canned form. First of all, I'm telling it, don't ask me. Then I'm going to tell it that I want to run on 1 MPI rank. And I'm going to tell it to run only my center of mass test. If I run this cell, you can see what outputs to screen. You can basically see the menu that the test suite system would have shown you, that you could have actually chosen things for. And if you scroll again to the very bottom, you see something that's not so informative because it just shows you kind of the menu again. But scrolling up a little bit shows you the result of the test suite. So here, I ran my test today at 5 p.m. London time, I guess. There was one test that it ran. It was the off-center TAV test of the center of mass thorn, and indeed the test passed. So everything seems to be in order. I seem to have computed and created everything that I need for a full thorn that computes the center of mass using a reduction, and I've verified that the answers is at least not insane. And that's basically all that I wanted to show. If you find yourself playing around with this notebook, and it's in the repository, you can also download it. Here's a couple of things that you may want to try. So I've spent some time explaining that the math that I'm computing isn't really anything useful, but you can make it into something useful by computing the metric determinant and multiplying it into it. So that one is something that you can relatively easily do. More complicated would be, okay, actually set up a parameter file where you have a center of mass that changes. You can give the initial TOV star some velocity using these parameters, then make the parameter file run longer, essentially make a parameter file that looks more closely to the one that you used for the tutorial on Monday, and run it and check that the center of mass actually changes as the star moves across the grid. And then finally, this is a bit more thought. Suppose you want to have a code where you don't necessarily have to have 3 time levels in hyperspace row because you're stingy and you don't want to spend the memory. What would you have to change? If you made such a change, what kind of restrictions on use would you get in your thorn? Which output can you still trust? Which output isn't good anymore? And the hint here is blacked out. If you mark it, then you should see what the hint says. And that's it for me. Thank you.
All right, Roland, thank you very much. If people have, oh yes, virtual hand claps, please. If anyone has any questions, please raise your hand or type something in the chat. Again, Roland is going to be around to answer questions in the subsequent days. Please make use of that time. In some ways, this is probably, well, this is the most advanced Cactus programming you will see during this workshop. Tomorrow, for maximum contrast, we will be programming Cactus with Python through NeRPi+, which should be the simplest way. And I encourage you all to drop in for that. Does anyone have any final comments or questions for the day? The question is, why did you put multi-declare CCTK arguments in your C subroutine, Roland?
So they depend on the mode that you're in. So if you scroll up here, so I have 3 in total. I have one that's here. That one happens in local mode. And so I need this one to actually get the values. If it says declare, so it declares the variable, but it also assigns values to the pointer. So I'm looping over each component, and in each component, the pointer for, say, row will point to a different location in memory. So the variable value actually changes. That's why I need to have it in here. And then I need to have another declare CCTK arguments here, because I'm outside of the containing scope in C. So whatever variables were declared in here have gone out of scope. So I need to do it once more to get access to the global variables when I want to use them here. And by the same token, I need another one down here because I'm again outside of the scope of that parentheses here. You could, if you wanted to, move this thing to the beginning, have it here.
Wouldn't that break your loop?
It wouldn't break the loop, but
would it shadow it?
It would shadow. Yes, that's why I'm not doing it, because the compiler sometimes warn about shadowed variables. It would be legal C.
Okay.
But you would shadow, yes.
All right. Anything else? All right. Thanks again, Roland, and thanks everybody for coming to the workshop today. And we hope to see you all again tomorrow.